I'm going to talk about residual errors in CANopen communication and some ideas we found. Very brief background. Different standards which are related to the machinery automation, which is my background, they clearly define certain requirements. I just collected few of them. And then the main reason behind this presentation is long experience on so-called common engineering understanding. Many people in machinery automation are saying that CANopen can be used only for the control applications, which are, let's say, applications where there is no relationship with functional safety. But still, from the very early publications from Bosch, since late 80s, define that one of main design principles has been that there is never undetected communication failure during the vehicle's life cycle. And as a consequence, majority of the control engineers, they have understood that any performance level cannot be achieved with CANopen. And then, in the analysis I have been involved during the last 15 years, there's a significant effort put to model masquerade errors and protection schemes against masquerade errors. And then, the most funny stuff. Those control engineers, they think that 4 to 20 milliamp is the best communication system in the world or in the universe. And that's the only possible basis for functional safety. And if, even for a normal control system, they think that even SIL 1 requires a lot of application layer safeguards at the top of CANopen. And also, interesting statement is that the less devices, the more dependable system from communication point of view. And at least I got a big question marks based on this. But let's start. The functional safety standard provides this kind of view. There's actually 3 functional blocks to be analyzed: input, processing, and output. But not only those. It's also clearly defined that also interconnection means shall be analyzed. And in the, let's say, more traditional control systems, it's quite simply because there's only single standard covering inputs, outputs, and analog communication means. In network communication, things to be analyzed are just the same. The only difference is that there's different standards for input and output devices and separate standards for the communication. At least in Finnish industry, majority of the analyses are based on the railway standards. And that may be the reason, because the standards are saying that these analog communication means are typically covered, or they are typically performed simultaneously by analyzing the outputs and the inputs. But they shall not be forgotten, as typically has been done. Then, this is a drawing based on EN 13849. There's a certain failure modes defined already in the standard. And there's a clear statement that if, for example, warranty feedback from the field reveals something else, it should be considered. And that's why we can clarify that there's, in addition to short circuit, also higher ohmic conductance shall be considered, because there can be deformated cables, dirt inside connectors, and so on. They are the most typical failures. And even the sensor failure in the milliamp signal can be corrupted by other failures, which are quite typical. And the rest. And based on these, we can clearly compute the diagnostic coverage by means of functional safety standards. It's far below 60%, which means none as a category. That is combination of the standards and based on almost 20 years experience in machinery industry. It's clearly like this. And then, cable does not know whether there is analog or CAN communication in the cable. The failure modes in the physical level, they are just equal. And there can be also in the CAN lines, short circuits, conductance, or in another direction there may be short circuit and or breakages. But majority of those failures can be detected by MAC layer, link layer, or application layer. And the reason, or because of the packet communication, the physical layer occurrences are not analyzed. There's a generic fault mode defined. And in the literature, there has been harmonized fault modes independent of the communication technology. And here I have listed in the left side fault modes, typical symptoms in CAN-based networks, and then some additional safeguards provided by CANopen. As we can see, duplicates are the most difficult one to detect. There is no safeguard for that. But majority of the rest, CANopen provides one or more additional safeguards. And of course, there's incorrect sequence and addressing. They are not so relevant in CANopen networks. And in the first stage, to be understood this problem, because the earlier analyses, they were more or less analyzing CRC performance and forgetting fixed fields and fields affecting on the DLC and other stuff. And in each analysis, those people have forgotten the CANopen application layer. They were analyzing CANopen networks just as a CAN layer networks without CANopen safeguards. That's why my starting point was to think about communication errors. And based on the earlier analysis and publications, I just took the different fault modes. And I took the residual error as a one category to be able to done some mathematical analysis. And then for the others, there's quite a many useful safeguards for use of which I have a long experience and a positive one. But then, now we focus on residual errors. Because we are talking CAN today, there's three options. Either ID can be broken, payload data can be broken, or CRC. And then we get certain categories. CRC failures when only the CRC is failing. And then masquerade failure when at least CAN ID is changed so that it looks like another valid CAN ID. And then corruption may be corruption of payload data, but not ID, and maybe also CRC. And if we have a corruption failure, or corruption residual failure, we still have plausibility checking if we are not using the full value range allowed by the data type. But if we are using only sub-range, then based on the meta-information of the signal and CANopen well-defined design process, we may get some safeguard also for that. But quite often, no way we are using the full signal range. Then we get through a single update, which is faulty. And then the masquerade failures. They may, because in typical control systems, we are using very small subset of the available ID space. That's why majority of the probability don't give any effect, because the CAN ID, the target CAN ID is not in use. But if we get the match, the CAN ID is transformed to another CAN ID which is in use. Then PDO mapping provides us a great tool for detecting if the if the PDO is too long or too short. It's depending on the implementation, but basically there is, from CANopen point of view, there's well-defined safeguard for that. In the application layer, because our PDO mapping discards invalid length PDO, then we get just our PDO timeout. Simple. But if also DLC is same, we have same amount of payload data, then we come back to the corruption and we get single faulty update. And there was quite clearly available numbers, except this level. And another writer of this paper was my ex-colleague, mathematician, who made some experiments. Our problem was which was the distribution between CRC, corruption, and masquerade failures. The only possibility was to analyze, based on the bit error probability P, that which are the raw probabilities. And after that, it was easy to compute the proportion of the residual errors falling into the masquerade or corruption. And we got this kind of values. And the absolute worst case values are here for masquerade and corruption failures. As you can see, as long as we are using the worst case values, we are very pessimistic, so we are on the very safe side. And then the big picture. This is the very common knowledge how to get from bit error probability to masquerade error probability. And I was lucky, I found one interesting paper written by some Italians in 2004. They have measured bit error probability of CAN network in different EMC conditions. And based on the long-term follow-up, I recognized that the average error condition is quite close to the machinery automation error environment. So we get good knowledge of the bit error probability. Then we get the message error probability. And then, very early days of CAN, it was, that equation is available in one paper written by Bosch people, and it has been included also in the CAN 2.0 specification from Bosch. So that's proven fact. And then we can include, we need to handle masquerade and corruption errors separately because they are quite different. And here we can see that effective masquerade error probability is quite small. And then the final residual error rate for CANopen. And here we transform from probability to rate to get probability of dangerous failures values. And these portions are computed based on the equations from previous slide. And in the safety analysis, we are interested in values defining dangerous failures per hour. And of course, safety standards give us some specifications for different SIL levels. And this result is quite interesting. By using correct bit error probability values or realistic ones and correct modeling, we got a result that if each signal update is required to keep the system safe, then with standard CANopen communication without any CANopen safety, we can easily, based on this value, we could easily reach SIL 3, which is more compatible with the experience in practice. And the typical implementation principle is that signal corruption hardly introduces visible effect, but not any danger. Then we get even more interesting results. Our statement based on this computation is that even standard CANopen communication is actually not limiting thing by means of functional safety. Of course, in certain conditions, if we have very hard requirements, some application safeguards may be required. And of course, there may be different kind of systems. But then, diagnostic accuracy. One requirement in the functional safety is clear indication of the faults. If we have analog stuff, no way. If we have two-channel system, we get information that we have some failure somewhere, but we need 2 out of 3 mechanism to detect which one is failing. But in CANopen, we can, based on combination of PDO and heartbeat, we can distinguish between different kind of failures. And if we have single failure somewhere, we get quite exact location of that. So, diagnostic coverage. The more we have CANopen devices in the network, the more we have reference points all over the network, the more accurate diagnostics we can achieve. But in the analog world, the more complex system, the more complex to diagnose, unfortunately. And then also the error behavior is different. In CANopen is, by its nature, it's fail silent if configured correctly. If there's significant communication failures, we just cannot messages through. It fails silent. But in analog communication, they are continuous time signals. As long as they are within the allowed range, the consuming device cannot detect anything. And then, when we were building up the equations, we found out nice design approach safeguards. Just the principles to be followed during the design by which we can increase further the residual error capabilities. This is adopted from SREO. if we can assign PD or CAN IDs so that there's at least 2 bit values difference, then it decreases residual error probability more. Then, if possible, by other requirements, it will also decrease or increase the diagnostic capabilities if we can use intentionally different DLCs for different PDOs or group of PDOs. And then, if we can use RPDO mapping as a diagnosis tool, if a device does not require or consume the signals, still if we map everything from the RPDOs, we get 1 diagnosis point more by as many devices as possible. And then, very simple one. If we are using update cycle half of the required one, it seems to open the sky for us. And also, if we have state signals, we can distribute the values so that there's at least two changes at least in 2 bits. And based on even the old analysis made by Bosch, it is very obvious that more smaller devices is far better from error detection point of view than only few large devices. And then, because main focus of yesterday and today is in CAN-FD, we put a little effort also for that. Good thing is that Hamming distance is maintained, and actually there's slight improvement because all DLC values produce different frame lengths. It helps a little bit in detection of the failures. And also the small improvement in bit stuffing, because the CRC is computed also over the stuff bits. It gives some improvement, and also the fixed stuff bits in the CRC field provide something better. Thanks for that. And then a brief conclusion. Unlike common engineering understands in the machinery industry, basic CANopen communication is not limiting the functional safety. And with a single channel system based on only CANopen, without any analog communication, the dominating safety constraints are in the application software compilers, software process, not in the communication. And if there is analog communication, it is the absolute constraint. There is no benefit for improving the software processes and so on in the single channel analog systems. In that way, there is also no sense to use classified PLCs. And it was funny to find out that by its nature, CANopen provides excellent safeguards, which shall be considered in the safety analysis. And don't centralize, distribute. That's all, folks. Thank you, and do we have time for questions?